Welcome to Opengyan video series. This video is a part of the computer architecture video series in which we have seen till now the von Neumann architecture, the cache memory and instruction pipelining. In this video we will see about the CPUs versus the GPUs. Today's high performance microprocessors target the general purpose applications with different goals. In general, these general purpose programs have less parallelism, more complex control requirements and lower performance goals than rendering a pipeline. Consequently, the design goals we enumerated previously were not those addressed by the CPUs, and CPUs have made different design choices that result in poor mapping to the graphics pipeline that is needed in today's applications. CPU programming models are generally serial and they do not adequately expose the data parallelism in their applications. I might have thousands of variables in my application, but still the CPU is going to process only one variable at a time. CPU hardware reflects this programming model in the common sense that the CPU process take one piece of data at a time and do not exploit the data parallelism. They do an admirable job of taking advantage of instruction parallelism, but the degree of parallelism exploited by a CPU is much less than that of a GPU. Hence, we have to move for a GPU as and compared to a CPU. So, what does that GPU brings onto the table? GPU accelerated computing is the use of using a graphical processing unit together with the CPU to accelerate the scientific, engineering and enterprise applications. Because the CPUs target the general purpose programs, they do not contain specialized hardware for particular functions. GPUs, however, can implement special purpose hardware for particular tasks, which is far more efficient than a general purpose programmable solution that can ever be made. Finally, CPU memory systems are optimized for minimum latency rather than maximum throughput targeted by the GPU memory systems. We have seen earlier wherein these cache memory systems are being used in the previous videos. Lacking parallelism, CPU programs must return memory references as quickly as possible to continue making progress and to avoid the bubble in the instruction pipeline. Consequently, CPU memory systems contain several levels of cache memories like L1, L2, RAM, hard disk, so on. For the graphics pipeline though, maximizing throughput for all the elements rather than minimizing latency for each element results in better utilization of the memory and a higher performance of the implementation overall. For example, in this picture over here, instead of getting it one pixel at a time, I might rather go for a hazy picture at first and then a more clearer picture as and when it moves on. That is what a GPU brings onto the table as when compared to the CPU. Now that we had an introduction of GPU, let's see what does it do. The GPU does the geometry, the texture, the rasterization, the culling or clipping and the Z-cull. Geometry, the GPU is used to draw the shapes, the arcs, the polygons needed for the visual effects. A vase is seen as a parabola from the side view. It is more like an engineering drawing that we had all done in our college days in the perspective views. Texture, it gives the look of the surface like the smooth surface of a marble, the coarse surface of the walls of a castle, the waters of a ocean, the smokes in a gunfight of the game. All these textures are given by the GPU. Rasterization is the task of taking an image described in a vector graphics format or the shapes and converting into the raster image of pixels or dots that can be displayed on the monitor. Culling or clipping is the task of removing the frames that are outside the field of vision. For example, an enemy soldier lurking around the corner in a game is being culled or clipped. Z-cull is the removing the hidden surfaces. It is that of not showing the hidden item that is behind the wall. So all these things are being done by the GPU. Now that we have seen what a GPU does, let's see how it does it. The GPU accelerated computing offers unprecedented application performance by offloading the compute-intensive portions of the application onto the GPU, while the remainder of the code still resides on the CPU. From a user's perspective, the application simply runs significantly faster. A simple way to understand the difference between a CPU and the GPU is to compare how they process the task. A CPU consists of a few cores optimized for sequential serial processing, while the GPU consists of thousands of smaller but more efficient cores designed for handling multiple simple tasks simultaneously. Because the CPUs target a general purpose programs, they do not contain the specialized hardware for particular functions. GPU, however, can implement these specialized hardware for the particular task, which are far more efficient. Let's say for finding one pixel at a time. Finally, the CPU memory systems are optimized for caching. And all these things need not be done on the GPU. The GPU can simply concentrate on one pixel at a time, while the application code on the CPU can concentrate on the sequential code. As it is, when we have an application code, it all results on the CPU, but just 5% of the code, which is more intensive on the compute function, is offloaded onto the GPU so that it can be done parallelly. Now, this is what the internals looks like. We have a CPU on top, we have the north bridge and then the south bridge. From the north bridge, there is a DRAM that is being connected to it, and there is also the GPU that is connected, and the GPU is connected to the display. And we have a graphics DRAM which the GPU can access, and it need not rely on the system DRAM. So this is what the internals look like, and all this fits into that ALU that we have seen in the von Neumann architecture. So what does the result that it gets? Instead of drawing one pixel at a time on this smiley face, what the GPU does is gives out one shot of the Mona Lisa painting. Though hazy, it is far more better than this pixelated smiley face. Thank you for watching this video. Do join us at Facebook at facebook.com/Opengyan. Write to us at ping@opengyan.com. Thank you. Have a nice day and have a nice week. Bye.